Hello students, today we will discuss the topic of Stodola method from the subject of mechanical vibrations. So this topic is very important from the subject point of view. So I want everyone to see it very carefully and all the details so that you can understand it. So sorry for the background noise if any. So let's start. So our topic is Stodola method. Okay, so first of all, Stodola method is used to calculate the natural frequency fundamental natural frequency of multi-degree of freedom system. Multi-degree means where there are several degree of freedom, and there could be three masses, four masses, five masses, or more than that. Fundamental natural frequency. Fundamental means lowest natural frequency of the multi-degree of freedom system. So it is a iterative process as you have done in numerical method subjects. There are iterations, so it is also a iterative method. There are, we will follow some iterations. After doing some iterations, we will reach our solution stepwise. So this is an iterative process to find the fundamental natural frequency of the multi-degree of freedom or several degree of freedom system. So we need to follow some of the steps in this method. I will mention briefly what will be the steps. The first step will be to assume the suitable deflection curve. You will assume a deflection curve from your side. Deflection curve, like you can assume for 3 degree of freedom like x1, x2, x3. If there are three masses, 3 degree of freedom, it would be 1, 1 and 1. So the first step will be to assume the suitable deflection curve, and it always be 1, 1, 1. So there would be second step. Second step is to find out inertia. Find out inertia loading. Inertia loading, it means inertia force. Okay, as you know that inertia force F is equal to mass into acceleration. So if there is mass, first mass is m1, and acceleration, you know that omega square x1 displacement. Okay, negative sign we have omitted because it is in opposite direction. So this is inertia force F1. As you know that inertia force second m2 omega 2 x2, and there will be third for 3 degree of freedom m3 omega square x3. So three forces acting on it, since x1 is 1, x2 is 1 and x3 is 1, so we can write it as m1 omega square, m2 omega square, m3 omega square, all the inertia forces f1, f2 and f3. So that would be your second step. So first step was to assume the deflection curve. Second step was to find out inertia force or inertia loading. There will be a third step. Third step is to calculate the new deflection curve. You can say new deflection curve. So you will calculate new deflection curve, that is x1 dash, x2 dash and x3 dash. Here you will apply the formula from influence coefficients. As you know that deflection at point 1 is equal and load due to unit load at point 1. Deflection at point 1 due to unit load at point 1 F1 plus deflection at point 1 due to unit load at point 2 F2 plus deflection at point 1 due to unit load at point 3 F3. Similarly for second point, deflection at point 2 due to unit load at point 1. Deflection at point 2 due to unit load at point 2, deflection at point 2 due to unit load at point 3. So this formula we will apply here to calculate new deflection curve. Okay, a1, a2, a3 all are influence coefficients. You need to find out the influence coefficients according to the system. The structure of the system will define its influence coefficient, and forces you have calculated in the previous step, second step, force you have calculated. So you will put the value of influence coefficient and forces, and you will get the corresponding new deflection curve. Now in step 4, you will have to check whether the assumed deflection curve, this is your assumed curve which you have assumed in the first step, whether it is equal to the calculated deflection curve or new deflection curve, whether it is equal. If it is equal, then we can find the frequency and we will close the process here. If it is not equal, then we have to assume another deflection curve as a starting point, which we have calculated in the third step. So means that the process will again start. Step 1 you will follow again, but here assumed deflection curve would be the one you have obtained from the calculation in the third step, like which whatever you have obtained in the third step, that would be your first point, starting point to start the process again. And then other step is to find the inertia force, and then again you will find new deflection curve, again check whether they are equal or not, and in this way you will complete the Stodola method. Now we will do some question, do one question or two to make it more understandable. Let's see. So I will taking a question that you have to find the natural frequency of a spring mass system. Spring mass system, I am writing in short form. Like this is your spring mass system here given to you. Wait a second. So here is spring, and here is your mass, first mass, another spring, another mass, another spring, and another mass. So let's say it is M. It could be M 2M 3M. Okay, it could be M5 M6 M whatever. So we are taking this as an example, and let the springs are K and K. It could be any K2 K3 K. It depends. Okay, so these are the deflections, or we can say displacements. So we will start our Stodola method. The step 1 we will start, we will assume the deflection curve. But as we know that in the third step we need the influence coefficients, so it's better to calculate the influence coefficients initially before starting the question. So as we know that it is a 3 degree of freedom system, so we will write our influence coefficients in this way: 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. These are called influence coefficients. If you don't know, these are called influence coefficients, and it varies according to the given system. It varies according to the structure of the system. So you will take all the influence coefficient in which you see 1, like here this is 1 1 1 1 1. You will take all and put it equal. You will all equate them, and whether you see the system of spring mass system, you will write it as first inverse of k or reciprocal of k, and this is the value of the influence coefficient of all these influence coefficients. Now again here we are left with the influence coefficient. Now you will take the influence coefficients in which you see 2 of from the remaining ones, like we are left with a22, a23, and a32. We equate them, and we will calculate it as 1 by k plus 1 by k, means 1 by k of this and 1 by k of this, so it will be your 2 by k. So now we are left with only one influence coefficient, a33, So it would be 1 by k plus 1 by k plus 1 by k, means it is 3 by k. So we have calculated all the influence coefficients, and now we will start our Stodola method from the step 1. So in the step 1, as we know, it is an iterative process, so we will write first trial. So it's just a trial. Maybe we can find it in the first trial, or we have to do some other trials. It depends. So we will assume the deflection curve. Let's assume the deflection curve x1, x2 and x3 is equal to, as we know, 1 1 1. So we know that in the second step we have to find inertia loading, inertia force, you can say. I'm writing in short form. Inertia force calculation F1, it would be m omega square x1. Okay, so F2 will be m omega square x2, because m all m's are equal, so we are not writing m1 m2 m3. As we know that x1 is 1, x2 is 1 and x3 is 1, so it is m omega square, m omega square and m omega square. So all the values of the forces I have written. Now in the third step you calculate a new deflection curve. Corresponding new deflection curve, you apply the formula x1 dash a11 f1 plus a12 f2 plus a13 f3, and x2 dash, you know, a12 f2, sorry, a21 deflection at point 2, deflection at point 2 due to load at point 2 plus deflection at point 2 due to load at point 3. Always remember these formulas. Deflection at point 3 due to load at point 1, deflection at point 3 due to load at point 2, deflection at point 3 due to load at point 3. So just put the values of influence coefficient. You know that this is a11, a12, a13. We have calculated a11, a12, a13. This is 1 by k. So we will put the values here, and we know that f1 is m omega square, f2 is also m omega square, f2 all m omega square. So we're left with m omega square by k plus m omega square by k plus m omega square by k. It is 3m omega square by k. So we have calculated first deflection, and similarly we will put the values of a21, a22, a23. We have calculated the values of influence coefficient. From here we will pick. So a21 is 1 by k, so it is 1 by k, and a22 is 2 by k, so it is 2 by k. So we will write 2 here and k here, and again other one is 2 by k, so it is 2 by k m omega square. So it is 5 m omega square by k. Just put the values and find out the new deflection. Again we will put the values here, so I am directly writing the final value. It is like that. So we have calculated three deflection curves, this one and this one. Now we will see whether it is equal to the assumed one or not. So it's your assumed deflection curve. So the new deflection curve, you can write x1 dash, x2 dash and x3 dash. It is if you take the ratio, actually now it's better to take the ratios. You know that the assumed one ratio x1, ratio x2, ratio x3, this ratio is 1 ratio 1 ratio 1. So to compare, we will also compare the ratios. It is better. So the ratio of these three will be 3 ratio, here is ratio 3 ratio 5 ratio 6. So there is 1 1 1, there is 3 5 6. Again one step, we will take 3 common, or we will divide all by 3. So it is 1 ratio 1.66 after dividing 5 by 3, and it's divided by 3, it is 1 this. So this is the ratio difference we are getting after first step. So we can say that it is 1, first one is 1, here is 1, okay good, but second one is 1 but it is 1.6, so it varies. Third one is 1 and it is 2, it varies. So we are not done with the answer because the corresponding new deflection curve is not equal to the assumed deflection curve. So we have to do the second step. So we will go for the second trial. So it is second trial. So in second trial, your x1 dash, x2 dash, and x3 dash you will take as you have calculated previously. Like you will take it as 1, 1.66, and 2. The answer you have got. Okay. So now this is your first step, assumed deflection curve. You have assumed this one. Now the second step is to calculate inertia loading. So here is F1, F2, F3. But to change the name, because we have done F1, F2, F3 here. So to change the name, we will mark it as F1 dash, F2 dash, F3 dash. So inertia loading is m omega square x1, so m omega square x1, but here it is x1 dash, so x1 dash, m omega square x2, here it is x2 dash, m omega square x3 dash. So we are doing these x1 x2 as x3, x1 dash, x2 dash, and x3 dash. Okay, so we will put the value, it is m omega square, it is 1.66 m omega square, and it would be 2 m omega square. So we have calculated the second step we have done. So the third step would be to calculate the corresponding new deflection. So it will be 1 double dash x2 double dash x3 double dash. So we will apply the same formula for the influence coefficient. Deflection at point 1 due to load at point 1, deflection at point 1 due to load at point 2, deflection at point 1 due to load at point 3, like that. Same method will be followed as we have done in the first trial. So it is quite easy method, but may go sometimes long, sometimes lengthy. So it is like this. Okay, so we will put the values of influence coefficients f1 dash, f2 dash, f3 dash from here, f1 dash, f2 dash, f3 dash. Okay, one step I will complete, other I will write directly. So f1 dash is m omega square, but a11 is 1 by k. So it is 1 by 66, 1.66 m omega square, other 1 by k. So it is 2 m omega square and 1 by k. Okay, adding these we will get 4.66 m omega square by k. Again in this after putting the values you will get, I'm writing it directly, you will get this, and in this if you put the values you will get this. So these are the corresponding deflections you are getting after doing this step. So make it in a ratio form of a ratio x1 double dash ratio x2 double dash ratio x3 double dash. So x1 double dash is 4.66, ratio 8.32, ratio 10.32. So after dividing it all with 4.66, so it would be 1 ratio 1.78, ratio it would be 2.21. So this is the ratio. Again you can see it is 1, it's 1, okay good, it is 1.6, it is 1.7, a little bit variation, it is 2, it is 2.2. You can say that it is still not equal. If you want more accuracy you can have a third trial. If you do not want to have much accuracy and you have lack of time in your examination, so you can close it here also, because a little bit variation is there, but your answer would not be accurate if you not do the third trial. So it's better here we will do the third trial. So in third trial again the same steps, your x1 double dash is 1, x2 double dash is 1.78. We are taking from the previous step, like these values, we are taking these values which are coming from the second trial. So inertia loading, again F1. Here you will write F1 double dash because F1 dash you have done already. So we'll change the notation, F2 double dash, F3 double dash. So here you will find the m omega square x1 double dash, m omega square x2 double dash, and m omega square x3 double dash. So after putting the values, you will get m omega square and 1.78 m omega square and 2.21 m omega square. So again, new deflection curve you will get x1 triple dash here, x2 triple dash, x3 triple dash. So again, apply the formula like we have done for the influence coefficients, a11 f1 double dash plus a12 f2 double dash plus a13 f3 double dash. I'm not writing these because you can see these are the formulas again already marked here, so you can practice by your own. After putting the values, you will get this as your answer here in the first step. First x1 triple dash and x2 triple dash would be like this would be the value and this would be your value. So now again make the ratio. It is 4.99 ratio 8.98 ratio 11.19. So again divided by 4.9 and everything 4 point, because we are making 1 at the first step, so it is 1.79 ratio 2.24. Again check whether it is equal or not. It is 1, it is 1, okay, it is a little bit but it's okay, and it is also, so you can close it the trial here because they are approximately close to the starting value. So we are closing the third trial, so we will not do the first trial. So what you have to do now is, as you see all the ratios are equal, you can equate them. Okay, you can equate them like you can write x1 double dash is equal to x1 triple dash because they are equal, x2 double dash is equal to x3 x2 triple dash, x3 double dash is equal to x3 triple dash because they are equal. So you can equate this as 1, you can equate this as 1, you can equate this as 1.78, you can equate this as 2.21. So with any of the equation you can calculate omega, which is your target value, which is you have to find m omega natural frequency. So we will calculate omega by equating x1 double dash is equal to x1 triple dash. So we will write x1 double dash is equal to x1 triple dash. So x1 double dash is 1 and we are equating it with 4.99 m omega square by k. So after calculation we will get omega as 0.44 k by m under root radian per second. So that would be your answer. So you have done Stodola method. You can see there's a trial method, iterations we have done. Okay, the method would be same and it is easy if you practice. Again, a variation which you can face from the Stodola method is the questions like you have to calculate natural frequency. This is a variation, or another type of question, type 2 you can say. Method would be same, but the difference will be in influence coefficients. So if you have to find the natural frequency by Stodola method. Okay, which type of question you can see? You can see a cantilever beam here. So cantilever beam with certain masses. Here it is m2, m1, and this distance is given 0.18 meter, and this distance is given 0.30 meter. So you can see this question, if not other. Here the process will be same. First of all, sorry. First of all, as you see, it is a 2 degree of freedom system. So you will write influence coefficients like this. So these are 4 influence coefficients you have to calculate. So what you have to do for the influence coefficients A12 is equal to 21 A22. You have to write it like this. So for the first, as you know the formula of deflection of cantilever beam, this distance you have to take 0.18 cube divided by 3EI. This okay, this is the formula. If you don't know, you can see the deflection of curve chapter in the strength of material subject, deflection of cantilever beam. So here for this mass for 2 to it can take this distance 0.30 cube upon 3EI. E is Young's modulus and I is polar moment of inertia. Okay, so again for the other system you can have to take this distance, you can take 0.18 square and 3L, you have to take the L full length minus 0.18 divided by 6EI. So you have to calculate the influence coefficient in this way. You will calculate all these influence coefficient. After calculation of the influence coefficient, what you have to do is to go for the first trial. I am not going to discuss in full detail here because this question will be similar to the question we have discussed. I am taking just a few steps here. X1 and X2 you would assume as F11, F1 and F2 you will calculate as m omega square x1, m omega square x2, and new deflection curve would be x1 dash and x2 dash. So its formula would be a11 f1 plus a12 f2 and a21 f1 plus a22 f2. All you have to do is put the values of f1 and f2 here, and a11 a22 a22 a3, all these values of the influence coefficient, and you will get the new deflection curve. Okay, here the ei values will be given to you. E will be like this. In this example it is 1.96 into 10 raised to power 11 Newton per meter square, and I value it is given 4 into 10 raised to power minus 7 meter square. So these values are given. You can easily put the values and calculate the value of influence coefficient. Masses are also given to you. Like you have to fill the value of m here. Okay, so in this question it is given. In the previous question it was not given, so we have not put the value of m. So here m1 is 100, m2 is 50 in kgs. So you can put the value of m1 and m2 in this. Okay, x1 and x2. So after doing this you will get the deflection curve, which here it is coming as the ratio is 1 ratio 2.15. The new ratio is not equal to the previous one, so you have to do the second trial. Again in the second trial you will assume the frequency as you have obtained in the first step, then f1 dash and f2 dash, the same formula. Put the values of m1 and m2, x1 and x1 dash. Okay, and then again you will find the new deflection curve x1 double dash and x2 double dash. Again you will check until and unless the same deflection curve is obtained after finishing the calculation, you will not close the trial and you will keep on going the doing the trials. As you the both the frequencies become equal, you can again write we have done in the previous question that x1 triple dash is equal to x1 double dash. So in this way you will again find the omega value. So that would be the type 2. The only difference is the difference of influence coefficient. The rest of the method is same. So I hope you understand and you practice as well. If you have any question you can comment and ask me. Thank you guys, thank you so much.